This is topic 6.1, part 2. And this is trapezoidal approximation of area under the curve. And what we have already covered is rectangular approximations. So if we just took a look at what we've already covered, the area under the curve from 1 to 3, we started with 2 rectangles. And those 2 rectangles, we used left endpoints and had this area. Then and that was an underestimate, and then we used right endpoints and used this as our approximation of area under the curve, which was an overestimate. And then we used the midpoint. Let's just say the midpoint of both of those is there, and that was our height. And then that's about right there. That was our height. And then this was our approximation of area under the curve. Not really sure if it was an overestimate or underestimate. It's under here. It's over here. So just not 100% sure. We would have to compute that. So basically, we estimated the area under the curve with rectangles. So what we have already done are rectangular approximations. We used L's, R, and M's, and various N, which is the number of rectangles. And what we noticed as N approached infinity, now we just got larger, the approximate area looked like it was approaching the actual area under the curve. And that is very, very true. So as we increase the number of rectangles, our approximate area gets closer and closer to the actual area under the curve. So we come up with this general statement that the area under the curve is actually equal to the limit as n approaches infinity of the sum from I equals 1 to infinity, actually from 1 to n, because n is approaching infinity, of delta x, and let me put f of x first, f of c sub I times delta x. Now, what you might want to know is about c sub I. Well, c sub I depends on if you're using left, rights, or mids. Okay? So if you're using a left, and you would have here, let's see, C, if you're using a left, and you're going from 1 to 3, of course, for the left, you would use 1 and 2 as your x values going into the function. If you're going from 1 to 3 and you're doing a right, you would use 2 and 3. For the mids, you would use 1.5 and 2.5. So your c sub i's are those x values that you are plugging in depending on where you are. So c sub 1 would be this first left one here. C sub 1 would be this right one here. And C sub 1 would be this first midpoint here. And you would go all the way until you reach N. And it would stop by however many. So here's our C sub 1, C sub 2, C sub 1, C sub 2, C sub 1, C sub 2. And you would stop at 2 because n was 2 in that case. Now, when we take this limit to infinity, we get the actual area under the curve. That is the actual area under the curve. Okay? So, now we define the definite integral. So, this is very, very important. This is our lower limit of integration. This b is our upper limit of integration. F of x is called the integrand. And dx is our variable of integration. Okay? So, in this here is an integral sign. And what does that look like? It's an elongated S, which stands for sum. So that integral is going to give us the sum of infinitely many, infinitely thin rectangles. And that's what it's equal to. Now, you can actually find the sum. We could go ahead and write this up here. Let me put a star there. If you wanted to find the area under the curve, the actual area under the curve from 1 to 3, let me put it down here. You would write the integral from 1 to 3 of x squared plus 1, leave a little space, dx. And actually, you can find that using Math 9. Now, what is that going to give us? That's the actual area of all of our approximations that we've done. Now, I cannot bring up a calculator on here, but you can quickly put Math 9 in your calculator. You can put x squared plus 1 in your calculator and find that from 1 to 3, and you will actually see that that's 10.667 or 32 thirds. So we were getting pretty close with our previous estimates. You could go back and look at those values that we got, and you could see how close we were. Either we were an overestimate or an underestimate. Now, let's present the trapezoidal approximation. You might be asking, why did we just cover this actual area under the curve? Because now we're going to be comparing our approximations to the actual area. We could have done this from the beginning, but I think it's a nice blend of approximating area under the curve and then seeing the actual. So I introduced the trapezoidal approximation. So instead of rectangles, we're going to be using trapezoids. Now, your first idea and thought when you hear trapezoid probably is this. Okay? Most students think of that as a trapezoid. Okay? Two parallel sides, and then whatever the other two sides do, they can vary. I want you to imagine this trapezoid right here. Okay? We call this B1, this B2. You probably called this the height. And that area was equal to 1/2 height times B1 plus B2. And you probably already knew that. I'm going to take that trapezoid now and I'm going to stand it up. So this is the same trapezoid as this. Okay? Now, this is delta x. So instead of our being our height, we're going to call that delta x, the width of that. Then we'll go ahead and call this B1, or you could just do the y value on this side, but I'll write B1, and this is B2. Okay, so that area is now still the 1/2 that is part of the formula. That is not what we put in front of our rectangular approximations. That is part of the formula. And then we're going to have delta x. times B1 plus B2. Well, what do you notice? If you have a curve like this and you have these trapezoids that kind of follow along this curve, I don't know if I drew those right, but I think I did. What do you notice? You're going to use this side and this side for the first rectangle. Then you're going to use this same side again and this side for the second rectangular area. And then you're going to use this side and this side for the third. And then you're going to use this side and this side for the fourth. So what do you notice? You use double on the insides and singles on the outside. And that's why we will write our formula as the area under that whole curve is going to be 1/2 delta x plus this side, this side one time, this height twice, this height twice, this height one time. It will make sense. Let's go right to an example. So for the interval from 1 to 3, so again, we're back from 1 to 3, and we want to have a T2. That's trapezoidal approximation with 2 rectangles. Now, I'm going to do the best job I can here, but this is a straight line, and this is a straight line. So you can sort of see that those lines are above the curve. So I'm going to tell you, with trapezoidal approximations, you look at concavity to see. Concavity tells us if we have an under or an over estimate. And right away, you can see if we are concave down, we have an underestimate. And now, with this example, we are concave up, which means we're going to have an overestimate of the actual area. Now, if it's both concave up and concave down, it may be a mix, but you should be able to see right in here and right in here that's below the curve. Okay, so let's see if we can go ahead and write our formula for these two trapezoids. Okay, so I'm going to have a T2. And let's always compare our answer to this 10.667. And we can add these up on the calculator and you can do it along with me. Okay, so here we go. 1/2 times delta x. So delta x is 3 minus 1 over 2, which is 1. You already knew that. 1/2 times 1. So now we're going to write f of 1 plus twice f of 2 plus f of 3. So 3 and 1 are on the outside, and then this 2 is doubled up because it's used to find the area of this first trapezoid and this second trapezoid. Okay? So we have 1/2, and we can just plug these in right now. F of 1 is 2, and F of 2 is 5, but we need 2 of those, so that's 10, plus F of 3 is 10. And we end up with 1/2 of 22, which is 11. Okay, so that's our first trapezoid. Let's see what happens when n is 4. So here is not drawn very perfect, but of course trying to get the idea. Whoops, that was sort of a curve. And you can see these trapezoids are going to all have just barely above this curve because it's concave up. And so now we're going to have a T. I'll change colors just so that you can see these apart. This is a T4. We need to go find our delta x is b minus a over n. And these are now 1/2. So a T4 is 1/2 times 1/2. Okay, now let's do this together. This is f of 1 plus 2. Don't forget, we have to put this point, all of these x values, okay? And I should have put these 3 x values there. So 2f of 1.5 plus 2f of 2 plus 2f of 2.5, and now just 1 f of 3, okay? So doubles on the inside, whoops, doubles on the inside, I call those the interiors, and then just singles on the end. So if you can go ahead and add those. So we will have 1/4, and let me tell you how I put this in my calculator. I went to Stat, List, and under L1, I put a 1, 1.5, 1.5, 2, 2, 2.5, 2.5, and a 3. Here are my outers. Here's double my inside. And that way in L2, when I found Y1 of the L1s here in L2 and added them up, I got 43. So it's very, very easy. That's how I find it the easiest, is to just write down each one of these twice, and then one time with the 3 and one time with the 1. And I got 43. And when you divide that by 4, you get 10.75. So we are actually getting closer to that 10.667. Why? Because we're using more trapezoids. Okay? So now let's try a T6. Okay? I'll go ahead and change colors. So we have a T6. I'm going to go ahead and write 1/2 because that's part of the formula. And then delta x is still 3 minus 1 over 6. That's 2/6, so it's 1/3. So 1/2 multiplied by 1/3. Now, we don't necessarily have to make this sketch each time, but I'll tell you, it is pretty nice. And I'm just going to be approximating these. And you can see there's 3 there, and there's 3 there, okay? But sometimes I'll just make a number line. Let's see if this helps. So you may not want to make, at least I don't, each time. My left end point is a 1, and I'm going to end up with a 3. Now the trapezoid, you need all of those values. We're going to use them all, not like a left, using all left except for the last one, or a right, using all on the right except for the first one. With the trapezoid, you use all of those. And we have 1, 2, 3 in there. So we have a total of 6 rectangles, 1, 2, 3, 4, 5, 6 trapezoids. Okay, so what are these? If they're a third, this is 1 1/3, which is 4/3, 5/3, 6/3, 7/3, 8/3, and then 9/3 is 3. So we're going to take 1 f of 1 plus double f of 4/3 plus double f of 5/3, double f of 2, double f of 7/3, double f of 8/3, and then just 1 f of 3. Okay, so we have 1/6 times. So if you'll go back to your stat enter, you can clear those columns, and what you're going to put in is a 1, and then a 4/3, and a 4/3, and then
sorry for the delay there, folks. We can let classrooms go at this time.
We're going to put in 5/3 twice, and then 2 twice, 7/3 twice, 8/3 twice, and then 3 just one time, okay? And then you're going to program that L2 column to find Y1 of the L1s. And then you're going to find that sum of the L2 column. And I got 64.222, so let's write that down. And then don't forget, we have to divide by 6. And I got 10.704. Now, how close are we getting? The actual area under the curve is 10.667. We said we were concave up, so we were definitely an overestimate. We should be above the actual. Actual is 10.667, and we had 10.704. So as you can see, we're closing in on that actual area under the curve. So make sure you are practicing these methods with your calculator so that you are comfortable knowing how to compute each one of these, okay? So let's look at this next example. Given the definite integral, -1 to 2, 10 minus x squared dx, our integrand is this function. So what this really is the area under the curve under the f of x equals 10 minus x squared curve from x equal to -1 to x equal to 2. That's really what this is, and it's the actual area because remember that integral uses infinitely many, okay? So we are going to be putting this in our calculator in part C and using Math 9. Okay, Math 9, and that will integrate that for us. And we're going to get the actual area under the curve, okay? And I'll just go ahead and give that to you right now. From -1 to 2, 10 minus x squared dx, if you use Math 9, you will get 27 on your calculator. So 27 is the actual area under the curve, okay? So let's go ahead and see what they want us to do. Use the trapezoidal rule with 3 equal subintervals, and equal is important to approximate its value. So we are on -1 to 2, and n is equal to 3. F of x is equal to 10 minus x squared. So all of that's very important information for us. Let's go ahead and find delta x is 2 minus a -1 all over 3, and it will just be 1. So they are 1 wide. So we will be finding a T3. 1/2 is in the formula. 1 is delta x. Now, I always like to just make a little line, and this one's a little trivial, but we're going from -1, there's 0, there's 1, and there's 2, and we have 3 subintervals, so there they are, 1, 2, 3. So we'll be using all of these points in our trapezoidal rule, 0 and 1. So sometimes it's just nice to make a number line. Okay, so we have 1 on the outer, f of -1, plus 2 f of 0, plus 2 f of 1, plus f of 2. Okay, so we have 1/2, and I don't think this will be difficult just to plug these in, but please check these with your calculator. 10 minus -1 squared, 10 minus 1 is a 9, plus 2 times f of 0. F of 0 is 10, and 2 times that is 20. 2 times f of 1, it's the same as f of -1, but we're doubling it this time. So f of 1 is 9, and doubling that, that's 18. Plus f of 2, 10 minus 4 is 6, and we are not doubling that, okay? So now if we add that up, we would get 29. 35 plus 18, and we're going to be taking half of 53, and that
You have
would be
approximately 40 seconds to get to class.
26.5.
40 seconds.
Okay?
Hustle on up.
Now, is your answer from part A an overestimate or an underestimate? I just want you to think about that. 10 minus f of x equals 10 minus x squared is concave down everywhere. Okay? So, since concave down, remember, with trapezoids, I'm going to really exaggerate this, okay? Pretending like those were trapezoids, okay? It's going to be an underestimate. So anytime you are concave down using the trapezoidal approximation, you have an underestimate of the actual area. Now, were we correct? 26.5 is less than 27. So it really should make sense right now. What if these intervals aren't the same? We did an example like this with a rectangular approximation. I always like to get my widths on here right away. That width is 2, that width is 1, that width is 3, that width is 4. You can also make a number line and get those off of this if you'd like, but I think it's fine. So the rate at which customers are being served at Starbucks, I guess that's, should be Starbucks, but he's making a joke. It's given by the continuous function r of t. A table of selected values of r of t for the time interval 0 to 10 hours is given below. At t equal to 0, now this is important, they already had 200 customers served. So that's going to come in handy if we're going to look at the accumulation and possibly want to know how many customers are served when we're finished, which you can see that's the second question down here. Okay, so let's go to the first question. Use a trapezoidal sum with 4 subintervals. So n is 4 to approximate the integral from 0 to 10. So I want to really work on notation. The integral from 0 to 10 of r of t dt, because remember, those are selected values here, is about equal to a t4, because we're approximating with a t4, which is equal to, now, we can't find delta x. Don't use a constant delta x, okay? It's changing. The width is changing. So you do need to make sure you don't use that delta x formula because you're not know what to plug in anyway, okay? So we're still going to use our 1/2 from our formula. That is part of the trapezoidal formula. But we're going to multiply width times height for each one of these, okay? So for trapezoidal, we're going to first take f of 0 and then multiply by, let me go ahead and put the width first. How about that? So the width there is 2 times f of 0 plus our width is now 1 times 2 f of 2 plus, and actually, you know what? Let's just go ahead and add these. And I'm going to tell you why, because it's very difficult to get those y values off. They're written like that. Same thing we did. We have a width of 2. And we want to add 37 plus 44. You're going to like this. Plus, so we did the 2. 1 width, and we're going to add 44 plus 36. Are you able to see how we double up on this guy? It's kind of a good example. Plus, let's take that width of 3 times 36 plus 42. There we are, doubling up on that 36 again, plus 4, and we're only taking 48. One time. excuse me, we have to add something to that, but we're not doubling it. Okay, so we have 4 times 42 plus 48. That didn't make sense what I said. So here's 42 doubled up, but we never doubled up 48 and 37, which are these 38 and 48, 37 and 48. We never doubled up on those, but we doubled these because we had to use those sides again for the next trapezoid. Okay? Let's go ahead and add this up. And when you get to that, you should get 418. And I do believe that has that half in there already. You can check that. 37 plus 44 times 2 plus 44 plus 36 plus 3 times 36 plus 42 plus 4 times 42 plus 48. And if you do that out, you get 836 divided by 2 is 418. So that did include that 1/2. Now, here's the question. Approximately how many customers have been served after 10 hours? Well, that would be what you had served already at time 0. So at time t equal to 0, 200 customers had been served, and we've accumulated over time, and 418 customers were served from t equal to 0 to t equal to 10 hours. Therefore, 618 customers were served after 10 hours. And that concludes